Let p of x be a polynomial with rational coefficients such that when p of x is divided by the polynomial x squared plus x plus 1, the remainder is x plus 2. And when p of x is divided by the polynomial x squared plus 1, the remainder is 2x plus 1. There is a unique polynomial of least degree with these two properties. What is the sum of the squares of the coefficients of that polynomial? Okay, alright. Now, let's just try to express p of x in terms of these two conditions. So first, when p of x is divided by the polynomial x squared plus x plus 1, the remainder is x plus 2. So basically, in this case, we can rewrite p of x as x squared plus x plus 1 times some polynomial right here, m of x, which we don't know what that is, plus x plus 2, since this is basically the remainder. Now, we can also say that p of x can also be expressed as the second one, the remainder when divided by x squared plus 1. So in this case, we're going to call it n of x. Now we plus a term, and that term would just be 2x plus 1, I believe. So now, let's just look at these expressions. What can we see in common? Well, there's also an x squared plus 1 right over here. So basically, we have x squared plus x plus 1 times m of x plus x plus 2. And that can actually be expressed as x squared plus 1 times m of x plus x m of x plus x plus 2. So if these two equations are equal, then basically the remainder of this divided by x squared plus 1 must be equal to 2x plus 1. So now, this one basically just says that x times m of x plus x plus 2. Now this entire thing mod x squared plus 1. That must be equal to 2x plus 1. So now we can just subtract this part over there. Then we're just gonna get x times m of x mod is congruent to x minus 1 mod x squared plus 1. Now, well, this thing, what's it gonna be? Then this polynomial, the minimum, will actually just simply be x minus 1. And this happens when this thing over here, when this term is just, when this term is just simply x squared plus 1 minus x squared plus 1 plus x 1 times x minus 1. Yeah, just plus x minus 1. So this one have a k in coefficient, but when k is equal to 1, then this simply just becomes x squared plus x. So simply m of x is just equal to x plus 1. Okay, alright. So if m of x is x plus 1, then what can we deduct from here? So we know m of x, then we can just simply plug into this equation and we're done. So then basically the function p of x that we want is simply just x plus 1 times x squared plus x plus 1, then plus x plus 2. That is just simply equal to, we just expand this. Well, you know that it's actually kind of tedious, but we still have to do it to solve this problem. So x cubed plus x squared plus x squared plus x plus 1. Just make sure to not mess up in the algebra part, or else it will just be unfortunate. This just becomes x cubed plus 2x squared plus 3x plus 3. And now we got a polynomial. Let's remind us what we want to find. We want to find the sum of squares of the coefficient of the polynomial. So then this just simply gives us 1 squared plus 2 squared plus 3 squared plus 3 squared, which is just equal to 5 plus 18, giving us 23 as our answer to number 20. E. Now let's go to number 21. Let S be the set of circles in the coordinate plane that are tangent to each of the 3 circles, with equations x squared plus y squared is equal to 4, x squared plus y squared is equal to 64, and x minus 5 squared plus y squared is equal to 3. Now, these equations are all for circles, and I want to just be reminded about the equation of the circle. So basically the coordinate or the vertex form, then just check out one of my earlier videos. But basically the general form will just be x minus h squared plus y minus k squared. That is equal to r squared. And that is basically denoting a circle with radius r and centered at h comma k, which is obviously in the Cartesian plane. So now let's just try to graph this situation. So I have this graph. Now just sketch what is happening right here. So x squared plus y squared is equal to 4. Plug into the vertex form, we get that h and k are 0, so basically it's centered at the origin. And r squared is equal to 4, so r is equal to plus or minus 2, but I mean you don't want negative, so just 2. So this is basically denoting a circle centered at the origin with a radius of 2. What about this? Well, this one still we have 0, 0, and square root of 64 just gives us 8. So then this one will just be a radius 8, and I'll draw it to be more larger. I cannot draw a circle today. Okay, so now we have another condition, which is x minus 5 squared plus y squared is equal to 3. Now, because we actually have the value of h, so this one will be centered at 5, 0, and the radius will just be the square root of 3. Alright, so we got the circle, and let's just say that this point is 5, 0. So then the circle would be centered and looking something like this. So now, what are we trying to find? So let S be the set of circles in coordinate planes that are tangent to each of the three circles. So basically, we need a circle that is actually tangent to all three of these circles. So how would a such circle be possible? So first, we obviously can just have one of the circles to be like this. To be somewhat looking like this, which basically means that this circle, we just call it to be omega, then omega is actually tangent to the blue circle, or internally tangent to the blue circle, but it's also or externally tangent to both of the circles, so to both of the red circle and the green circle. So now, how are we going to find the radius? Well, let's just first draw all the possible circles. Excuse me, I just made a mistake on drawing this circle. So because it's 5, 0, then it should be centered at then it should obviously be centered at 5, 0, but I draw it to be like floating in the middle. So then the circle would just be landing somewhere right here. This circle, right over here. So now let's just draw all possible cases. So first, as I have just said, we can have a circle that's externally tangent to both of the circles, to both of the green and the red circles. And notice that because it's on the x-axis, so therefore it's actually symmetrical with respect to the x-axis. So basically, we can also have another circle that is right over here, that's located below instead of above. So now we can have one circle that's internally tangent to the blue circle and an external tangent to both of the circles. What are other cases? Well, we can also have a large circle that encompasses both of these circles. Well, actually, I think this is probably not possible. Yeah, you have a larger circle that actually encompasses both of these circles. So basically, it's externally tangent in this kind of manner, but so basically, these two circles are internally tangent to this circle, and this circle is internally tangent to the blue circle outside. And this will actually be one possible way. And because of symmetry, then we would actually have another circle. So let me just do casework. So we're going to just start with the simpler case, which is just this circle right here, right over here. So because we know that if two circles are internally tangent and we have their centers, and we draw a line that expresses the common tangent line of the two circles, then basically let's just call this to be S to be the center, to be the tangency point. Then S01 and O2 are in fact collinear points. So we just use this really important fact. Then we know that these points are actually collinear. And in fact, we can even see that this point is also collinear with the entire line. So this point also lies on this line, or this radius. Now we know that this part has a length of 2, so we can just say that this is r and this is r. So case 1 will just be 2 plus 2r is equal to 8. So r is equal to 4. No, r is equal to 3. Okay, that's the first case. Now let's go to the next case. Now we're going to go on to this case, which is just this large circle that encompasses both. Well, I mean, let me just redraw this diagram since it's not really realistic. Okay, so same idea. So we just make this to be the center. Then this is actually a straight line that connects both of these tangency points. So we have this length to be 2, this length to be also 2, and that this length will just be r minus 4, but we know that this length would also be r. So now we have, well, in fact, 2r minus 2 is equal to 8. R is equal to 5. That's the second case. And are we done? Well, not. Because, well, let me just denote this to be omega 1, this to be omega 2, and the outer side circle to be omega 3. Then we can have another circle in the fashion that we can have another circle called omega 4, such that omega 1 is internally tangent to omega 4, but omega 2 is externally tangent to omega 4, and omega 4 is internally tangent to omega 3. So this such circle will just be looking something like this. And in the same fashion, we can also have some circle that looks something like this. Sorry if there's a space here, but you get the idea that it's externally tangent to this and internally tangent to this. So how are we going to compute this radius? Well, this radius is exactly the same, because we can just draw this line and call this to be the center. And if we call this r, this is r minus 4, and this is 2. Then after you solve, then you get that r is equal to 5, which is exactly the same as this circle, except that we just basically reflects across the axis y is equal to x. And this circle, since this circle is externally tangent to this one, then we just get to draw a line like this. R, and 2. So this gets that radius is equal to 3. So basically, we have a total of 4 cases. And we can see that for all of the cases, we can literally just create a new case that has the same area but a different case. So we have to add all the 4 cases, add the area of all the 4 circles, but we have to multiply by 2 to address for the symmetry. So we in fact have two circles with the radius 5 square pi and two circles with the radius 3 square pi that we have just showed. So 5 square pi plus 3 square pi times 2, but don't forget about symmetry, so you have to multiply by 2 again. This will just be equal to 4 times 34 pi, which is equal to 136 pi, and that just simply gives us an answer of E, 136 pi. Thank you for watching, hope you enjoyed, and I'll see you in the next video. Goodbye.